The main challenges that are faced by the Limassol water organization is the fragmented operational data. For example, SCADA and telemetry data or smart water meters are stored in separate systems with no unified access. There is limited capability to combine these data sources for the monitoring of district metered areas, the DMAs, or for detection of anomalies like leakages or contaminations. And the slow and inconsistent workflows when they have to validate or share or use the data across technical and operational teams are also a challenge. At the moment, the traditional systems operate in silos, and this prevents a holistic understanding of the network behavior. There is no integrated pipeline to advanced analytics or decision support tools. There is an obvious need for a unified, standards-based ecosystem that ingests data, ensures quality, and feeds analytics applications. What the water data management ecosystem provides here as an innovation, it provides a harmonized data integration pipeline that automates the ingestion of telemetry, like pressures and flow, and also smart water meter consumption, for instance, into the water data management ecosystem portal. This enables seamless transfer of cleaned, already standardized data to analytics apps, supporting state estimation, anomaly detection, or other algorithms execution for selected DMAs. This facilitates cross-team access through an interoperable, fair-aligned data ecosystem. And as a result, we have faster, more reliable DMA insights through centralized integration of the SCADA plus the smart water metering data, improved leak and anomaly detection and operational decision-making thanks to advanced analytics for state estimation, pattern deviations, etc., and also strengthening of institutional readiness for digital transformation and the future EU data space participation. We're going to demonstrate some flows in the Cyprus pilot. After we have retrieved this data, we have the data sources connected, we can create these processing mashups. Here, if we go directly to the retrieved telemetry data of DMA 133 DMA, it's a simple row, a simple workflow that processes the information. Every data that enters this workflow will be processed, converted, and goes to the output. How we can retrieve this now? If we go to the flows, we have, let's go to the same DMA 133. This is the triggering. We define the triggering to be a scheduler every hour. And what it will do, it will take the version 6 of that mashup that we saw earlier, and the execution of this, the red box, will go to the data portal at a specific point using authentication as well for a specific organization. And these are the data sources. And going, for instance, to this data source, we see that the telemetry data that we have been pushing are here. DMA 133. So it's the data that we have been using for the pilot in Limassol. We are coming every day for quite a few months. By the time the data arrive in this portal, they are available to third parties through an API. This is the API. And the data is ready to go for the next step. We are ready to see now how we use this data in a third-party application, which is a Phoebe application developed in another project, DigiWater. We log into this application. And what we see here is that we have a number of network topologies. This is the DMA 133 in EPANet format with all the nodes and all the links. We have here a number of analytics tools because this is the purpose of this application. Let's see how we use this from the network monitoring. If we go to DMA 133, if we just try a tool, from the tools we say, take the pressure sensor placement executions, the one that we executed, and it gives us solutions here. There are 3 solutions for the placement, 3 in a Pareto front. For instance, one of the solutions is this. The white nodes here are the ones that are suggested as the optimal positions for this sensors in order to achieve detectability of leakages. If we go to component management, this is where we have all the components of all our networks. What we do, we upload the sensors, either we define, of course, which network. Either we upload directly from a file if we have offline measurements to test, because this is like a digital twin where we can run scenarios, or we have APIs. We have, among the APIs that we support here is the WATERVERSE portal, either for the telemetry data or for the smart water meters data. And this is how we connect to the WATERVERSE data portal that we saw earlier in order to retrieve the data, the real measurements, and enable the execution of the state estimations, etc.
From a technical perspective, integrating different data sources traditionally required a lot of custom work. WATERVERSE offered us a structured way to harmonize data and connect our systems with fewer complications.
What I appreciated most in the WATERVERSE pilot was the improved collaboration between departments. Access to consistent information will help us coordinate tasks and respond more efficiently to internal and external requests.
In operations, time and clarity matter. With WATERVERSE, we were able to bring real-time sensors and lab measurements into a single view.
For SMEs like ours, WATERVERSE creates real opportunities. Harmonized and accessible data allows us to deploy digital twin solutions faster and with higher accuracy. It lowers integration barriers for innovation.
WATERVERSE also supports better reporting and regulatory compliance, which is essential for the work we do every day.